All right, hi guys, and we are now starting with chapter 6. This is a 2-weeker all about electronic structure and periodic properties of elements. So this week we are only going through sections 1 through 3, and next week will be 4 and 5. So your homework won't be due until next week, as well as any labs and whatnot. Chapter 6 is pretty different from everything we've done so far. Um, Definitely one you're probably going to want to go through the lectures multiple times to help you understand everything. Take your time going through the examples and the homework and ask me any questions that come up. I understand this is a very tough chapter and, again, very different from what we've done so far. So there's just a picture of the Crab Nebula. It's the remnants of a supernova, this explosion of a star. We can measure some of the emitted light, the wavelengths from it, to identify some of the elements in it. So they've been able to identify things like S plus, sulfur, and oxygen 2 plus, and other elements that have come off of it. Which brings us to section 6.1, electromagnetic energy. So in this section, we're going to explain the basic behavior of waves, including traveling waves and standing waves, describe the wave nature of light, use appropriate equations to calculate related light wave properties such as frequency, wavelength, and energy, distinguish between line and continuous emission spectra, and describe the particle nature of light. So, starting off, the nature of light has been the subject of inquiry since antiquity. We've always wanted to know what light is, what it's made of, if it's made of anything, how it behaves. So, in the 17th century, Isaac Newton came up with the idea that white light consists of the individual colors of the rainbow combined together, and that it's composed of streams of really tiny particles traveling at high speeds according to his laws of motion. Going on in the 19th century, Thomas Young sent light through some very narrow, closely spaced slits to make interference patterns, but the he couldn't explain this with using Newton's ideas of light being a particle, but by using the idea of a wave, could explain it. And then we come to James Clerk Maxwell, and we have Maxwell's equations, where he came up with the idea that light was the visible part of a vast spectrum of what are called electromagnetic waves, or electromagnetic radiation. And then we have that particles and waves are connected in what we call wave particle duality. So light can act as a wave, but it can also act as a particle depending on what it's doing. So let's talk about what a wave is. A wave is an oscillation or periodic movement that can transport energy from one point in space to another. Okay, so this is a wave. Some examples: shaking the end of a rope. Okay, you can make a rope do that. Dropping a pebble in a pond, you make little waves that go out from the center. The expansion of air that accompanies a lightning strike. Okay, that's a sound wave. So, in every one of these cases, kinetic energy, movement, is transferred through matter, whether it be rope, water, air, while that matter actually really stays in the same place. For instance, if you are shaking the end of a rope, you have this wave traveling through it. You're making a wave, but the actual rope pieces itself, it's not going anywhere, right? It's still in your hand. It's not leaving your hand. It's staying essentially in the same place. Now, waves don't only travel through matter. We have electromagnetic waves, okay, and these are consisting of an electric field. So these aren't matter, they're not traveling, they're not actual things, it's energy. And they're oscillating perpendicular to a magnetic field, which are perpendicular direction of travel. Don't worry too much about this. But they can travel through a vacuum at a constant speed, and this is known as the speed of light. And we abbreviate the speed of light with a lowercase c, and it is equal to 2.998 times 10 to the 8th meters per second. Roughly, you can also say 3 times 10 to the 8th meters per second. So this is the speed of light in a vacuum. May as well just say it's the speed of light. And this all electromagnetic waves travel at this speed. Doesn't matter the size of the wave itself, which we'll talk about. They all travel at the same speed. So there's some different characterizations of waves. We have the first, which is wavelength, and this is the distance between two peaks or troughs in a wave. So if this is my wave, one wavelength, this is a wavelength, okay? Lambda is the symbol we use, and this is also lambda, okay? Trough to trough, peak to peak, it's the same wavelength. That is the wavelength. The frequency is the number of successive wavelengths that pass a given point in a unit time. Usually it's 1 second, for instance. Okay, so wavelength tends to be given in either in units of meters or nanometers, centimeters, that type of thing. Frequency is in inverse seconds because it's like waves per second, and waves isn't really an actual unit, so it's inverse seconds. And then we have amplitude, which is 1/2 the distance between the peaks and troughs. So again, the unit for frequency is cycles per second. Okay, I said waves, I meant cycles, which is inverse seconds, or the hertz, Hz. Oftentimes we use megahertz or gigahertz because 1 hertz is actually very, very small. So mega is 10 to the 6th, giga is 10 to the 9th. So if we multiply a wavelength times the frequency, we get the speed of the wave. And frequency, by the way, the symbol for this, it's not a V, it's actually called nu. Okay, it's another Greek symbol. It kind of looks like a V, but it's actually a nu. So, and like I said, all electromagnetic radiation or waves travel at the same speed, which is the speed of light. So the speed of light is equal to the wavelength times frequency. C equals lambda nu. So wavelength and frequency are inversely proportional to each other. As one goes up, the other goes down. Higher wavelength, lower frequency. Lower wavelength, higher frequency. Which makes sense, right? Because if you have a big wavelength, it's going to take a little while to get through one cycle. When we get through one cycle, there's less waves. But if we have a smaller wavelength, going through the same amount of time, a much higher frequency because more waves are able to pass through that point. So here's visual examples for you, showing wavelength, frequency, and speed. Okay, wave with the shortest wavelength has the highest frequency. And then we see they also kind of show us amplitude as well. 1/2 the height of a wave from peak to trough. Okay, so if we have, so the height of the wave divided by 2 is the amplitude of the wave. So let's talk about the electromagnetic spectrum. And this is the range of all types of electromagnetic radiation, more so than just the visible spectrum of light. The visible light, which is the colors that we see, is only a teeny portion of the spectrum. And each color of visible light has a specific frequency and wavelength associated with it. So here is a a picture showing the different wavelengths for the electromagnetic spectrum and where some of these wavelengths are used. And this is, again, only really portions of it. We have gamma rays. These are the smallest electromagnetic waves that we know of. Okay, and so this is like cosmic rays, and PET scans of the brain tend to be used, are used in this gamma ray. Then we go a little bit larger, so going from left to right, we're getting bigger in our wavelength. We get to X-rays. Most of us have had an X-ray done at least one time. And then the ultraviolet range, an example is dental curing. So if you've had a filling or a crown and they do a light cure, it's using ultraviolet light to cause the filling stuff to actually harden. And then we go to the visible light, which is what we see. Then we get to infrared. Things like our remote controls use infrared, as well as night vision. Not too much in the terahertz range, but then microwaves, of course, microwave ovens. Our cell phones tend to use them. Radar, Wi-Fi. This all tends to be microwave. So, and if you look, the size of a microwave, it tends to be about 1 centimeter to 1 foot in wavelength. So much bigger compared to, 10 to the negative 12th meters. And then the largest type, we have the broadcast and wireless radio. So things like AM radio, these are really big wavelengths. Okay, so we're talking 10 to the 3rd meters. So you can see a huge spread of types of waves, their sizes, and their frequencies. Okay, and at the very top, you can also see kind of just a representative sketch of these sizes of the waves, and you can also see how the frequency, goes up as the wavelength goes down. And also the lower wavelengths have higher energies about them. So let's look at some math. I know you guys love that. A sodium streetlight gives off yellow light that has a wavelength of 589 nanometers. What is the frequency of this light? And they were nice enough to remind us that 1 nanometer is equal to 1 times 10 to the negative 9th power. So starting with the equation for the speed of light, c equals lambda nu, and we want nu. So we need to divide both sides by lambda, so nu is equal to c times lambda. So we have what's a weird looking 2.998 times 10 to the 8th meters per second, divided by, we can go ahead and say 589 times 10 to the negative 9th meters. Makes things a little easier that way. Or you can do it this way too, that's perfectly fine. And you get 5.09 times 10 to the 14th inverse seconds, or hertz. Either one works. Also notice that they wrote the speed of light, instead of putting meters over seconds, they put meters times inverse seconds, which is the same thing, because s to the negative 1, that's still saying 1 over s. So you could say either m over s like that, or ms to the negative 1. Either way is perfectly fine. And then here's some radio and cell towers used for giving us the radiation for our phones. Also, just want to point out that the word radiation is not necessarily a bad thing. It just means energy. And then let's see, this is just showing how we can use AM, which stands for amplitude modulation. So this is AM radio. And frequency modulation, which is FM radio, for transmitting radio waves. So on that note, let's talk about interference patterns. These arise when light passes through narrow slits closely spaced about a wavelength apart. So what happens is you have like you have a couple slits here, and you send your light through it. And then what ends up happening is it splits the light to where it can either add or cancel each other out. So where, oops, I didn't draw that right. Let's try this again. So here's my first wave. And then our second wave, I do something like this. And where you have a peak from one hitting the trough of the other, you end up with a dark region. So if you were looking at the pattern this makes, this would be a dark area. So this is destructive interference. They're destroying each other. Where if you have the two peaks or two troughs that coincide with each other, this is a bright region. So there's going to be some that are a little dimmer than others, but the brightest regions, this is called constructive interference. They're adding together. So we can't explain this happening using classical mechanics, which is what we've talked about up till this point. Here's a much better picture showing what I was trying to show you. Passing light through through double splits. So these bright ones are showing the constructive interference, and then those dark spaces you see are the destructive interference. Now, not all waves are traveling waves. So the light we've been talking about has been traveling. We have what are called standing waves or stationary waves, and these stay within some space. So for instance, playing a guitar, okay, those guitar strings become standing waves. They're fixed. So they're fixed at the top and at the bottom. And when you pluck the string on a guitar, what's happening is you're actually creating waves. There's different types of waves that it'll make. Okay, and as that string is vibrating as a wave, it can't go anywhere. Okay, so it's a standing wave. And these are really important for understanding electronic structures of atoms and molecules. If you have a string that is held where it's fixed at its two endpoints, just like a guitar string, you have a one-dimensional standing wave. So these are all examples of one-dimensional standing waves. And then if you notice, we can only have these kind of nodes happening at the half value. So if we took a half of this one big wave, then we can have a little node here and have two little waves. Then we could divide each of those kind of in half and then half again. Okay, so they can only have these half wavelengths forming these nodes. We'll talk more about that as we go. Where it's not moving, so the ends and those inner parts are called nodes. So a node is where something is not moving. So only waves that have an integer number that we're calling n of half wavelengths between the endpoints can form. Okay, so these are integer numbers. Integer meaning, 1, 2, 3, 500, 250. And if you have fixed endpoints, then the number and the type of waveforms is fixed. There's only so many things you can make. It restricts what you can do. It's an example of B. I don't know what B it's talking about. Only discrete values from a more general set of values are observed. Okay. So we also have what are called harmonic waves. And these have one or more points between the two endpoints that are not in motion, and these are called nodes. So that was where, you have your two endpoints, and you have something like this. And you have a point here that's not in motion. This is a node. Okay, I should probably do it like this. There we go. So where they don't move are called nodes. let's see. The other thing I just want to point out, let me go back to this picture. This is called quantization. And basically this tells us that only discrete values, so only like a number of 1, 2, 3, it has to be just an integer number from a general set of values can be seen. Okay, so this goes along with nodes. These are quantized. Oops. Now, if you have a flat surface and you're like have a vibrational pattern, this is a two-dimensional standing wave. So this is something like a speaker. Okay, you may not be able to see them unless you maybe sprinkle with some powder or something. And then what's going to happen is it's going to move that powder in the shape of the waves. So with the one-dimensional standing waves, the nodes were points on a line. The two-dimensional, they're lines on a surface. So here's an example right here. This is a two-dimensional standing wave. Those lines are the nodes. So let's talk about black body radiation and the ultraviolet catastrophe. Sounds scarier than it is. Don't worry. No one died. So sunlight consists of a big range of wavelengths that form what is called the continuous spectrum. And then we have a black body, which is a convenient ideal emitter that approximates the behavior of many materials when it's heated. So it's a model. A good example of a black body for observing black body radiation is a metal oven that we can heat to high temperatures. So here's an example for you. The kind of brown-orange line is the intensity of different wavelengths of electromagnetic radiation or light that's coming from sunlight. And so you see the different wavelengths in nanometers here. And it also shows you where it stops at between the UV and the visible spectrum. And then it's modeled in blue by a 5,250 degree black body spectrum, which is that blue curve. And it does a pretty good job at matching this distribution from the sun. So one thing that has been noticed is the maxima, which is that peak. Okay, so from this peak, the maxima shifts to shorter wavelengths as we increase the temperature. So it goes to the left as temperature increases. Different theoretical expressions as functions of temperature fit the observed blackbody curves well at longer wavelengths. Okay, so at lower temperatures. But at shorter wavelengths, at higher temperatures, they're not matching up very well. And this is called the ultraviolet catastrophe because these functions, these expressions that we're trying to model this data did not work for shorter wavelengths. So the models basically fell apart. So here's an example of the black body distribution curves for some different temperatures. And you can see what they were saying. As the higher temperatures, our maxima is further to the left at shorter wavelengths. So as you see, as our temperature is going down, that maxima is shifting to the right at higher wavelengths outside of the visible spectra. So around 1900, we have Max Planck, and he came up with this expression for black body radiation that actually fit the observations exactly within error. So science saying something exact is a little iffy to say, but with an experimental error, he was able to fit the data. And the way he did this was by saying that atoms can vibrate. And they vibrate at increasing frequencies or decreasing wavelengths. Okay, remember they're inversely proportional as the temperature increases. So we increase the temperature, they start vibrating with a higher frequency or smaller wavelength. So they start going like, you know, from like so to really fast, kind of like a kid when you give him sugar. Okay? And one thing he couldn't explain, but that he assumed, was that these atoms had to have a quantized energy. That he really, again, he couldn't explain it. He just kind of was like, yeah, this is it. I'm not going to tell you why. Don't ask me why. This is just it. And he came up with the equation of E equals NH nu. Okay, where N can equal 1, 2, 3, and so on and so forth. So these are the quantized energy states. H is now called Planck's constant, equals 6.626 times 10 to the negative 34th joule seconds. So it's joules times seconds. Really, really, really small. But this is also why energy quantization hadn't been seen in larger phenomena, because this constant is tiny, but it makes a big difference as you get into much smaller energy states. So that was one paradox that had to be fixed. And then the next came around with the photoelectric effect. And this is actually where some work from Einstein comes into play. One thing that had been seen was that electrons could be ejected from the surface of a metal. But to do that, you had to have some light with a frequency greater than some threshold, some minimum frequency, to get it to do this. But one thing that was noticed was that the energy of the electrons didn't care about how bright the light was, but it did care, it increased with increasing frequency of light. So brightness, whatever, we don't care, but the actual frequency of the light is what actually mattered. So in classical wave theory, the energy of a wave depends on the intensity, not its frequency. But the opposite was seen. So Albert Einstein took Planck's quantization findings into the particle view of light, and this is actually what won him the Nobel Prize. Not E equals mc squared. It was actually the photoelectric effect work he did. So light striking a metal surface should not be looked at as a wave, but instead as a stream of particles that we define as the photon, and we will talk about. So the energy of a photon, so photon is like a little packet of light. The energy depends on the frequency. So starting with Planck's formula, E equals h nu, and we know that C equals lambda nu. So then if we substitute nu equals C over lambda, substitute that in for nu here, we get that E equals hc over lambda. Then going back to E equals h nu, or is that hv? Sorry, that should be h nu. Yeah, it's h nu. Okay. Electrons are emitted when hit by photons with enough energy. So it needs to have enough energy greater than some minimum energy to get them to take off. Greater the frequency, the greater the kinetic energy, so the greater the motion. Okay, that's given to the escaping electrons by when they collide. So when that photon hits the electron, if it has a higher frequency, it's able to give more energy to the electron for it to take off. This still isn't fully understood how light does this, but we call it the wave-particle duality. Light can act as a wave, but it can also act as a particle. So if the photon doesn't have enough energy to make an electron bounce off, nothing happens. So at like a higher wavelength of light, something like red colored light that has a wavelength of 700 nanometers, it hits the metal and nothing happens because it doesn't have a high enough frequency. Once we start at a higher frequency, something like 550 nanometers or green, we see some electrons coming out. And with a velocity, okay, or a speed equal to maximum of 2.96 times 10 to the 5th. And then we go to an even higher frequency and we can see those electrons come out with an even higher maximum velocity. Okay, so the energy or the speed, that kinetic energy of the electron is going to increase with the energy of the photon. So example 6.2 is doing another calculation, looking at neon signs. And what's happening is we're seeing radiation coming off of an excited neon atom. So let's say this radiation has a wavelength of 640 nanometers, and we want to know the energy of the photon being emitted. So we're going to use Planck's equation that has wavelength, okay, so the derived equation, and convert the units of nanometers to meters so that we have all of our units matching up. So that's one thing to make sure that you fix. So E equals hc over lambda. H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds, times speed of light, divided by lambda. And again, we have to make it into meters from nanometers. You could do it like this, or you could just write 640 times 10 to the negative 9th meters if you want, because 1 nanometer is 10 to the negative 9th meters. Plug that into your calculator and you get 3.10 times 10 to the negative 19th joules. Now I want to take a second, use this as a great example of the use of parentheses on your calculators. You could put all of this into a scientific calculator, but you need to use parentheses correctly to do it. So while putting this in, you have a numerator and denominator that you need to make sure are separated. So you need to have a big parenthesis, and then you're going to do a second parenthesis for this. You would put 6.626 exp, or whatever your exponential button is, negative 34, and then close that off with a parenthesis. So that way it knows, okay, this stays together. And then hit our times button, another parenthesis, 2.998 exp 8, close parenthesis. And now we're going to close that other big parenthesis. So that way the calculator knows, okay, this is all the numerator. And then we hit our divide by sign. And then another parenthesis, 640 exp negative 9, close parenthesis. And then hit equals. A lot of times when I have students who aren't getting the right answer and they're insistent they typed everything in right, it's a parenthesis issue. So always make sure you're checking your parentheses and seeing where everything goes. All right, so another issue that we had with light and energy, scientists struggled with understanding light being emitted from atoms and molecules. Because what happens is when you heat a solid, liquid, or a gas enough, they radiate some energy as light. So photons. And these photons come off with a big range of energies, producing a continuous spectrum where you have an unbroken series of wavelengths present. But, so instead of a continuous spectra, we can also see discrete or line spectra where you have these very narrow line widths in a spectral region. And this is what happens for things like atoms. So if you, again, heat a gas, for instance, at a low pressure with an electric current, you produce a line spectra. And every element has its own characteristic set of lines. So you might be able to actually identify some unknown compound just by looking at its line spectra. There's a neon sign. We'll look at a picture of line spectra soon. But each emission line has a single wavelength of light. So you have a scale with your wavelengths, and they're in different colors, of course, but what you would find are these little single lines, and those each represent a single wavelength. And so this also tells us that the light that's being emitted has discrete energies. It has very set energies. And this was super puzzling to scientists, because in classical electromagnetic theory, this can't happen. It should only be continuous spectra. So again, we have another issue that we have to solve. So here's an example of continuous spectra versus some line spectra. So if you were to look through at white light, this is what it would look like. You took a prism and looked at it. And then here's some line spectra for sodium, hydrogen, calcium, and mercury. And you can see just these single bands that are being produced. And then there's just black everywhere else. So there's very set energies that are needed for photons to be emitted, and there's only certain energies that work for different elements. Which brings us to 1885. Johann Balmer came up with an equation that related the 4 visible wavelengths of light emitted by hydrogen atoms. Okay, so if we go back, hydrogen, it's the second one here. See, there's 1, 2, 3, 4 wavelengths of light that we can see. And he was able to relate this using whole integers. 1 over lambda, so the wavelength is equal to some constant k times 1 over 4 minus 1 over n squared, where n can equal 3, 4, 5, or 6. So there were other lines found in the UV and the IR regions, but this is focusing on the visible. And then Johannes Rydberg went and worked further on this, because there were those other lines in the UV and the IR, and he came up with a more generalized empirical formula that predicted every single one of hydrogen's emission lines, both the IR, the UV, the visible, and that's 1 over lambda equals R infinity, which is called the Rydberg constant. So there's its value, times 1 over n1 squared minus 1 over n2 squared. N1 and N2 are integers. Okay, and N1 is less than N2. So there's another thing.